Hi again, it's Mike Sklash, and we're here with the third of our webinar series on groundwater, and today we're going to talk about groundwater models, and I am presenting today with my colleague Matt Schroeder. Just some background if you haven't been involved in the previous two. My background is I've got a bachelor's in geological engineering, a master's and PhD in earth sciences from the University of Waterloo, where I studied hydrogeology. I was a professor at the University of Windsor for about 15 years. In the last few years, I've been an adjunct professor at Lawrence Technological University in the Department of Civil Engineering. I've been senior hydrogeologist with Dragon since 1992, and I tend to do expert work, both the U.S. and Canada, and also I'm involved in some large projects. I'll let Matt introduce himself.
Hi, this is Matt Schroeder. I'm a senior engineer here at Dragon, and I've been working here since 1994, and got my civil engineering and environmental engineering degrees from the University of Michigan, and do a lot of remediation work. Earlier in my career, I did quite a bit of modeling, and so that's where I get drawn into this presentation. Worked on both sides of the border, so done expert work in both the U.S. and Canada. And happy to be here with you today.
So we're doing this series that tries to help you with resolving a groundwater contamination issue the first time, and the key is the first time. And we had two previous webinars, chemical fate and transport, a couple of weeks ago, conceptual site models actually 2 weeks ago, and groundwater models today. They're all somewhat related. So during the webinar, if you have any questions, please email Alan Hahn or ahahn@dragon.com. And if we have time, we can discuss live at the end. Otherwise, you can email directly to me, msklash@dragon.com, or Matt, mschroeder@dragon.com. So why discuss groundwater models? And in small brackets there, I've got with the contaminant fate and transport that we talked about before, and conceptual site models that we talked about before. Well, groundwater models help to demonstrate that you understand the site that you're dealing with, and that makes decision makers more comfortable with what you're saying. It also, models help to facilitate selection of remedial options, and they'll help you to determine your contribution, if any, to a groundwater contamination plume. So if there's multiple contributors, it's a good tool for helping you figure out what your responsibility is. So today we're going to talk about what is a groundwater model, the modeling process, and the mini case studies. And I'm going to pass it over to Matt, who's going to take you through the number 1 and 2.
So there's lots of different types of models that we use in our industry. We're going to talk about groundwater flow and contaminant transport models today, but there's also models for the unsaturated zone, so the part of the subsurface between the ground and the water table. There's models for simulating multi-phase transport, where you may have free-phase liquids traveling along with water or air or gases. There's also air models that we use to model releases from discharges to, say, out of a smokestack or something like that. Any of these types of models could be either analytical or numerical. So rather than talking about the whole gambit, we're going to focus on the groundwater flow and transport models, because those are the ones that we probably use most often in our daily work. So the process is kind of shown schematically here in this decision tree, and the way we start is kind of getting together and defining what the objectives are for our model, and from that, actually not from that, but you develop separately a conceptual model, which is the understanding that you have of the physical system. And I'll talk a little bit more about that, and I think Mike has discussed that in some of his earlier presentations. From there, you select your model code, and that's where you try and find the model that best fits what your objectives are and what your understanding of the system is, so your conceptual model. And then you go through the model design, and then from there you take your model design and you test it, and that's through calibration, verification, sensitivity analysis. I'll talk a little bit more about each of those steps further on. And you look to see if the results of this testing meet your criteria, and if not, you may need to go back and do this whole process again, and even might need to collect more data. So this can be an iterative process as you go through, and then once you finally have the model that you are comfortable with and meets your criteria, then you go to simulation and try and use your model in a predictive fashion. So of all these steps, in my opinion, the conceptual model is the most important. It forms the basis for your model design, and from that you can do an independent confirmation with data. But the conceptual model is really the backbone of your computer model, and is an important step in the process. So as far as defining objectives, a model can be used for a lot of different things. We've used models to help support site closure. Say when you want to leave some contamination in place, and you use a model to demonstrate to the regulators that it's really not going to go anywhere and no one's going to be exposed to it. We use models to help design remediation. A pump and treat is the easiest example, but you can also look at if I did some source removal, what effect would that have on the down gradient plume, and how does that affect my decision making with respect to designing remediation. You can use models to help determine when or where a release occurred, and as Mike talked about, to determine your responsibility for what's out there. We've also used models to help justify a modeling frequency that might be a little less often than what the regulators typically would shoot for. The default that you hear from most regulators is they want quarterly monitoring. Well, a lot of times that just doesn't make sense for how fast the groundwater and the contaminants are moving. So we've used models to justify modeling or monitoring frequency as long as 3 years. So this is our kind of basic first step in a conceptual model, and this is called a block diagram. And basically, if you were to carve out a chunk of our site and be able to look below the ground, this is what you would see. So what we try and depict on this is the geology, which is these brown and yellow and hatched layers down here. We try and show the water levels, so that the dark blue dashed line here is where the water is in our system here. Not really shown on this, but sometimes you might show where recharge occurs. If you have, say, a surface water body that might be a recharge, or an area where you think you might have water coming into the system, that can be important to show on a block diagram. Chemical distributions is something you can also show. If we had impacts in the unsaturated zone, we might show them on the cut through the block diagram here, or if we had a product on the water table, we might show it on the block diagram. Potential sources, you can see we have 2 underground storage tanks shown on the surface of our block diagram. Any other features affecting the flow are also good to put on there, such as rivers, lakes, if there are faults that might affect the subsurface flow. All those things are good to put into the conceptual model and can be shown on the block diagram. Another part of our conceptual model is making sure we have a good understanding of the flow and being able to depict that. So this is a diagram of groundwater flow. So these dark blue lines here are equipotential lines, and basically those are areas that have the same water elevation. And so these black arrows are drawn perpendicular to those lines because the water flows perpendicular to these equipotential lines. And so what we're looking at here is flow direction and gradient, which is gradient is shown by the distance between the lines. So you can see it's a higher gradient here because there's less distance between the lines, a lower gradient over here, and that will be important later when we start looking at our model results. You might have multiple of these to describe a particular flow system. In the example that I'm going to go through, there was really only one water-bearing unit that was important, so we're using one flow system. But if you have multiple aquifers in a system, you may have multiple flow diagrams like this to describe what's going on. So after you've got the conceptual model, you need to decide how you're going to pick your model code. Is transport an important aspect to the question you're trying to answer, or can you get away with just a flow model? Advection describes kind of the bulk flow, whereas advection and dispersion may be important for a situation where you've got more complicated flow conditions. Is your flow mostly one-dimensional, or do you need to go all the way up to a three-dimensional system to be able to describe what's going on? Steady state or transient, are things changing, and does that affect how you're trying to answer your questions? If so, you may need a transient model that can simulate different conditions at different times. And then numerical or analytical complexity of the model, those are all nuances that you have to consider also. In general, my philosophy is to follow the KISS principle. The simplest model that can meet your objective is probably the best one to use. Generally, the higher level of complexity of the model itself, the more information you're going to need to be able to match reality and be able to use it in an effective manner. So I'm going to go through an example, and this example is a remediation design. And so what we had here was the conceptual model that I showed earlier, that system, and we ended up using a numerical flow model called ModFlow. And ModFlow is probably the most commonly used groundwater flow model in our business. It was designed back in the 70s by USGS and has been thoroughly vetted, and it's widely used in our industry. And in this instance, we used a particle tracking code called ModPath to simulate the chemical transport, and I'll show you a little bit of that a little later in the presentation. And we did it in a two-dimensional version because there wasn't a lot of vertical variation in our system, so we could just use the X and Y planes to describe, and we used a steady state system. So step one was to design our model, and first thing you do is you take your site and you have to break it up into a model grid. So that's these grid lines that are shown throughout here. And you can see we have a finer grid near our potential source areas, and then a wider grid as you go outward from there, because it's more important to have better, closer information in here where things are going to be changing more quickly than further out in the model. For each of these grid nodes, or these squares here, we assign model properties. So things like the hydraulic conductivity, the recharge that may be occurring over those, porosity, storativity, all of those properties of the soil itself get assigned to each of these nodes, and they can be different for each one of them. We also put boundary conditions in, and the boundary conditions help to constrain the model and help define the flow. And so down here where there's a gravel pit, we put in a value for the water level there that's a fairly constant value. Similarly, on the up gradient side of the property, we put in a fairly constant value here. And that helps to make the flow go from the upstream side down to the downstream where we know that it goes. So the model, as you run the actual model itself, gives a water level elevation for each of these cells. And we can use those elevations to create the equipotential contours similar to what we did with our field data. And so the first step in checking to see if your model is appropriate is to do a calibration by inspection. And so we take our flow system that we got of the model and compare it to the flow system that we saw from our field data. And you can see that the shapes are pretty much the same. You can see that we have a higher gradient down in here, where we see a higher gradient down here. So just looking at it, it looks like it's replicating the actual flow system pretty well. The other way that we check our calibration is by comparing the water levels that are predicted by the model to the water levels that are observed in the field. And ideally, they would all fall along this black line where they'd all be exactly what they're supposed to be. You can see that, we aren't exactly on the line, but we're fairly close in this instance. And typically what you would do is define how far away from this line is acceptable, a certain percentage away from this line, and then you try and get all of your heads, or at least a certain percentage of them within that acceptable range. Back when I was first in my doing some modeling in my career, we would actually set the models up and let them run overnight, because they would take anywhere from 8 to 12 hours to run. These days, models, the processing speed has gotten fast enough that that's not typically a limitation on how many of these you can do. And so you can run a lot of model runs and really optimize your parameters very well. And some of the models even have features where you can input ranges and let the model kind of optimize the best fit within your reasonable range for your model parameters to get real close to the observed data. So the next thing that we do once we have a calibration that we're comfortable with is do something called a sensitivity analysis. And sensitivity analysis is the way that you test the parameters of your input that are uncertain. And so you'll vary those input parameters and see what effect they have on your model results, and also whether those effects on the results affect the conclusions that you're making. And if you find that they are having a big effect, these uncertain parameters, then it may drive you to go and collect some more data to try and make sure that the model is actually predicting reality, especially if it has a big effect on your conclusions. So step 2 in our example here is to check the flow model and see if it's actually accurately predicting where the chemicals are moving. So here we have, this is the observed groundwater plume from our field data, and they're covered up, but one of the tank systems was right here, and the other tank system is right here. And so the way that we're going to look at this is by using particle tracking, and as I mentioned before, that's the mod path that we use to track the chemical movement in our model. And you can think of particle tracking like a golf ball on a putting green. So what we do is where these red dots are, we drop a ball here, and it's going to follow the contours of the water table to an endpoint over a certain amount of time. And so we had an idea of when the releases could have occurred, so we put some particle tracks around this UST and around this UST, and made sure that the tracks that we saw that came off of those initial spots matched fairly well with the groundwater plume that we saw it in the field. And you can see it's kind of the same shape, and that's what we're looking for here. So this is an independent confirmation of our model from the flow data that we used to set up the model. So step 3 is, now that we're comfortable with our calibration and we've checked the model with sensitivity analysis, we can apply the model to the design of the remediation system. And so what we're looking for here is, if we were to put in a pump and treat system, kind of what would be the best design for the pump and treat system. So for this instance, we use particle tracking again, and this time we put particle tracks around the outside of the plume and tried to figure out where the best place was to put pumping wells to be able to capture all those particles that were on the outside of the plume. And so answers or questions that you can answer using the model like this is, where do we position these wells that makes the most sense? What pumping rate do we need to be able to capture the whole plume? And would more or less wells kind of be more cost effective to capture this plume over the time that the remediation is going to happen? So that was an example of the way we used a model for remediation design. Mike is going to step back in here and talk about a different project where we used a model in a little different way.
So this is a mini case study of a site that we worked on a number of years ago where we did modeling to look at a remediation, how we can kind of re-engineer a remediation. So I've subtitled this, How Our Client Convinced the Regulators to Allow Them to Turn Off Their Groundwater Pump and Treat System. And I'll go through trying to explain exactly what we did here, kind of in quick order. So there was a release of trichloroethylene at this property. This area was used to make aftermarket car parts, and they used trichloroethylene, which is carcinogenic at low concentrations. It's used as a metal cleaner. It was released, and it got into the ground and impacted the groundwater in this area. Property boundaries, the down gradient property boundaries, are along here to the south and along the train track, and the consultants who had designed the remediation system previously had used pump and treat, and basically you put a pumping well into the groundwater and it sucks groundwater around it into the pumping well, and you take that water and you treat it in a treatment plant, and you would protect the down gradient property boundaries from releasing impacted groundwater. So when we got involved, we noticed there was this steeply incised stream on the property. There's a landfill here that was also a potential source of impact. So the problem was we had a sandy aquifer. The soil was sandy, and it was impacted by trichloroethylene. They had used pump and treat for the TCE impacted groundwater. Pump and treat costed about $100,000 per year in that order to remediate, and it would go on forever. And the regulators wanted our client to meet background at the property boundaries. So you couldn't release anything from the down gradient property boundaries in the groundwater. So our objective, after we started looking at this, and we thought maybe you can do this better. Can we shut off the pump and treat? So we studied the hydrogeological information, which direction the groundwater was flowing, the topography, where the impacts were, and came up with a concept of what you might be able to do instead of pump and treat. And one of the things we knew was that the concentrations that were allowed in the surface water in that stream that the regulators allowed was higher than the allowance in the groundwater. So with pump and treat, and there were a number of wells, these were the ones that I can still see, the groundwater basically is drawn to the pumping wells, and then they pipe it over to the remediation system, and by doing that, you prevent contaminated water from leaving the site. However, that costs about $100,000 a year. This is what I pictured the groundwater to do if you shut off the pumping wells. It would all go to this stream, which, if you evaluate the hydrogeology, you see that the stream dominates groundwater flow. So I had to prove with my colleagues to the regulators that you could turn off the pumps, the water would go to the stream, and the stream concentrations would be acceptable to the regulators. So we designed a ModFlow model two-dimensional, the same one that Matt used with particle tracking, and we put in all sorts of input parameters based on the work that had been done previously at the site. We calibrated the model and did sensitivity and simulations, as Matt mentioned you needed to do. And we got the groundwater flow to model to simulate what was happening when the pumps were working. Then in the model, we turned off the pumps and looked to see where the water went, and it went to the stream, as we suggested. So we talked to the regulators and showed them what we had found and asked them if we could do a trial turning off the pumps, because groundwater doesn't move there very quickly. So if we turned off the pumps for a couple of weeks or a couple of months, it wouldn't make a big difference. And we did that, and the groundwater flowed to the stream. So we actually verified that the model worked by seeing that the groundwater flowed to the stream when we turned off the pump. And then we monitored stream quality to see if it was acceptable. The result was that the regulator accepted our model. They accepted our CSM, which is our conceptual site model. They understood that we understood what was going on, and we turned off the pumps. The client saved on the order of $100,000 per year because the only costs were for monitoring. So we had to go out and monitor the stream water and the groundwater along the perimeter versus pump and treat and monitoring. So that was a very successful use of groundwater modeling to kind of re-engineer a remediation that is costly and would last forever. So, you know, Matt had mentioned that when he was younger, he would have to wait all night for his model results to come through, and I'm a lot older, and I had to wait a week for my model results to come through. But now you can get models that will give you almost instantaneous results. You know, you know, 3 or 4 weeks worth of work that you had to do a long time ago, you can do very quickly. But the important part is you need the fundamentals right. It's kind of garbage in, garbage out. So your conceptual site model has to be reliable. Your code has to be one that is well recognized and is appropriate for the work, and the design of your model has to be right. You have to go through all the steps to convince the regulators or the people making decisions that you've checked out how varying parameters will cause your model to change, and the sensitivity analysis and so on. And then you have to look at your model results and your data, and you have to decide what you can believe. Ideally, they come out the same. Sometimes you'll find models that will give you data that don't make sense based on what your, models output don't make sense based on a comparison to the data. So you have to make sure that you go through all the steps, have a model that's well thought out, and you have to go back and make sure that it is a believable model. So just want to mention that in a week or so, Alan will have this webinar recorded on our website, and just if you want to look at other things that Dragon Corporation does, a lot of the modeling we do starts as a peer review. We look at other models and see what they've done right, what they've done wrong. You can find that on our website as well. So on behalf of Matt and myself, thank you for listening. We will stay on if you have some questions. We'll stay on for a couple minutes and we can answer those. If not, thank you for joining us.